Harbin. Welcome to Video Notes 10.2. This is going to be a long one, but it'll be fun. We got a lot of formulas. Best thing to do, write these formulas down, okay? Read chapter 15, but there's some stuff in here that's not in your book. So, okay, let's talk about solutions. Alright, so solutions. Looking at this solution of Kool-Aid, oh yeah. What's the solute and the solvent? So we got the solute is the sugar and the flavor, and the solvent is water. Tap water. Oh, you're like, that's not a solution, but it is. The solvent is water, and the solute is all of the ions I could put in there to keep it good. All right, 98% rubbing alcohol. Okay, so 98% means that most of this solution is rubbing alcohol. So the actual solute is the water, and the solvent is the rubbing alcohol, because there's 98% rubbing alcohol. So you have to know what the solute is and what the solvent is and what they make together for the rest of this. All right, oh yeah. So time to concentrate. Solution is solute plus solvent. The concentration describes how much solute is in the solution. So we could have a concentrated solution. What does that mean? Well, that means you got a lot of solute dissolved in a little bit of solvent. It's very concentrated. Okay, a lot of solute in a little bit of solvent. Okay, concentrated. Dilute. Okay, not a lot of solute. Okay, dilute, not a lot of solute. Kind of fun to say. All right, so this is just very, very qualitative, right? I'm sorry. Yeah, very, very qualitative. We want to quantify it. So let's start quantifying and describing. Concentration helps us describe how much of the stuff is in there. Okay, so you can have a lot of solute or a little solute, and instead of just saying that, you can figure out its concentration. So some are rather obvious. If you have dark Kool-Aid or light Kool-Aid, this one is more concentrated because it has more solute dissolved, right? Right. This one is less concentrated. Less concentrated. If you have a stinky lab partner or not a very stinky lab partner, well, if they're stinky, there's a lot of concentrated stinkiness about them. And if they're not very stinky, then they're dilute. All right. Rusty, tasty water or tasteless water. If you taste it, it's more concentrated than if you don't. Okay, so concentrated, dilute. Okay, might hear some noise. My family's watching the Avengers right now, so you might hear that in the background. All right, what's more concentrated, 70% SpongeBob fans or 50% SpongeBob fans? Well, if you have a room full of 70% SpongeBob fans, there's a high concentration of SpongeBob fans there than here. Okay, not my official card, but hey, I can't show you my official card. So, how do we really describe concentration? The most common way is called molarity. You've seen it on the bottles. You see the capital M. Now we're finally going to know what it means. Here's what it means. Memorize this. Write it down. Memorize it. Molarity is moles of the solute for liters of solution. It's a ratio, because remember, solutions are very well mixed. So the same proportions are in each part. So you could have a concentration or molarity of a solution no matter how much of it you have. It's a ratio of solute to liters of solution. Capital letter M is for molarity, and it said molar. Oh, look, it's a little molar. Get it? 1 molar. This is a 1 molar solution. Haha. All right, so now, so let's practice. If you have 25 grams of calcium fluoride dissolved in 150 milliliters of water, what's the molarity? Well, molarity is moles of solute per liter of solution. So we got to change the moles of calcium fluoride into grams. So then we take a look. Where do I get this 78.08? I didn't make it up. I went to the periodic table. All right, for 1 mole. CaF2. So we find out that that is 0.320 moles of calcium fluoride for every 150 milliliters. Be careful. 150 milliliters is for every 1,000 milliliters. It's 1 liter. So it's 0.150 liters. The molarity is 2.13 molar calcium fluoride. Okay. All right, how many grams of CO2 gas are 500 milliliters of 2.5 molar Dr. Pepper? This is a neat one. So what does this mean? It means there's 2.5 times 10 to the negative second moles of carbon dioxide for every 1 liter of solution. Okay, that's what that means. So if you have 500 milliliters of solution, then that's really So because molarity has liters, we say it's 1,000 milliliters for every 1 liter. And then every 1 liter of Dr. Pepper has 2.5 times 10 to the negative second moles of carbon dioxide. Okay, so what's the concentrate, or what, sorry, how many moles is that? Well, here, we can even go one step further and say we want to find grams. So we say, well, then for every 1 mole of carbon dioxide, there's 44.01 grams of CO2. Where did I get that? PT, periodic table. All right, so then you do 500 divided by 1,000 times 2.5 times 10 to the second times 44.01. We find out that there are 0.55 grams of carbon dioxide if the concentration of carbon dioxide is 2.5 times 10 to the negative second. How can a gas be the solute? And carbon dioxide is nonpolar, so what's going on there? High pressure. High pressure puts gas into liquid, all right? So, all right, that was molarity. Say it with me, molarity. Molarity, which is capital M, which is moles per liter. Okay, there are other ways to do concentration. So here's another one. It's called molality. Look at that L. It's different. Molality. That's a little L. Molality is moles of solute. Again, hey, that's the same. This time, though, it's kilograms of solvent on the bottom. And the reason this is used is so that we can find out how solutes affect solvents. So you have to know how to do this concentration. Okay. So molal is a lowercase m. All right. So lowercase m. Just remember that. Find the molality, careful with the L, of 25.0 grams of sodium fluoride dissolved in 750 grams of water. Okay, so this is solute. This is solvent. All right, so we would say 25.0 grams of NaF times, where am I going to get this? If you're saying periodic table, you're right, 41.99 grams of NaF for every 1 mole NaF. And then that will give us the moles of NaF. We find out it's 0.595 moles. All right, NaF. But now to get molality, we need to divide it by kilograms of solvent. All right, so let's look up. So this is 750 grams. 750 grams of water times 1,000 grams per kilogram. Right, those conversions are going to be handy. So that's 0.750 kilograms of water. So we find out we have a 0.793 molal solution of NaF. All right, lowercase molal. Hard to say it. Molal. Hey, a train. You hear that train going by? Honk the horn. All right, so molality has the L, and it's molal lowercase m. Molarity is the R, and that's a big capital M. All right, so what mass of water is needed to dissolve 0.00250 grams of NaCN to make 0.050 molal poison? All right, because this will kill you, NaCN. So we want to know how much water. So we want to know how much solvent is needed. This must be the solute here, and that has to be in moles. So 0.00250 grams of NaCN times, let's see, how much is NaCN? Where we got to go? We got to go to the periodic table. We find out 49.01 grams of NaCN for every 1 mole of NaCN. And so there are 5.11 times 10 to the negative 5th moles of NaCN. All right, what's our definition of molality? Is moles over kilogram solvent. All right, mole solute over kilogram. So right now we got moles solute. We need kilogram solvent. Wait a second, that's what we're trying to find. So what do we do now? All right, so let's set up a ratio. 0.050 moles of solute for every 1 kilogram of solvent has to be equal to 5.11 times 10 to the negative 5th moles of NaCN. Okay, that's what I got there. For every X kilograms. That's what we were looking for. So now I'm going to cross multiply 0.050 moles times kilograms equals 5.11 times 10 to the negative first mole kilograms. And then we got to divide to get X. So I'm going to divide this by 0.050 moles. Looking at moles cancel out, I'm left with kilograms, and I find out that I will need 0.00102 kilograms of water, which is 1.02 times 10 to the negative third kilograms H2O to make that solution. Okay, so that's how you do it. You gotta watch the math, you gotta know your definitions. Okay, density can help us find other things. So if we know densities, you'll be all set too. Alright, so when we make that hydrochloric acid that we use in the lab, we it comes from 12.1 molar HCl that has a density of 1.18 grams. For this solution, let's calculate the molality and let's calculate the molarity of the solution. Okay, so how are we going to do that? Well, we need, for molarity, we need moles per liter. For molality, we need moles per kilogram solvent. So let's do molality first. We need moles of solute per kilogram solvent. And this is lowercase m. Okay, what do we know so far? Well, we know that we have 12.1 molar. Right? That means 12.1 moles for every 1 liter. Okay, how can we use that? Well, we want this many moles, right? We want to figure out the molarity of the solution and the percent by weight of it. So we know how many moles we have, right? So we could say, well, we have the 12.1 moles of solute in the solution, and for every 1 mole there's 36.46 grams of HCl. How did I get that? You bet your periodic table. Alright, so that tells us we have 441.6.1. Let's just go like this. 442 grams of HCl. Alright, so what do we do with that? Alright, well, HCl is our solute. Okay, in order to get molality, we need to know the mass of our solvent. So we have to take, we have to figure out how many grams of water are in this. So here's what we do with the density. We say, well, if we have 1 liter, so this means 1 liter. Okay, if we have 1 liter of solution times the fact that 1 liter is 1,000 milliliters, and here's where density is going to come in. Then I also know about my solution that 1 milliliter is 1.86 grams. How do I know that? Because that's what density. I said 1.8186. I lied. 1.18. There we go. Now we're back on track. Liters cancel, liters, milliliters cancel. I find out that there's 1,180 grams of solution, because that's the density of my whole solution. Here's how many grams of solute. So if I say 1,180 grams of solution minus 442 grams of solute, I'm going to figure out how many grams of solvent I have. Okay, so then I would take my 1,180 minus my 442. I find I have 738 grams of solvent. Now I can figure out my molality. Why? Because I have my moles, 12.1 moles, and I have my grams of solvent. I just have to change that to kilograms. So then I would say 12.1 moles of solute for every 0.738 kilograms of solvent. I find out that my molality is 12.1 divided by 0.738 gives me 16.4 molal solution. So that was part A. Okay, the molality. Now part B is a percent by weight of HCl. Oh, percent. Yay, it's another way to talk about concentration. Percent is always part over total. Part over total. So what's the part of a solution? The solute. So we need mass of solute. Let's see. 442 grams. Figured that out earlier. and then divided by our total, which is our mass of our solution, divided by the 1,180 grams of solution times 100 is 442 divided by 1180 times 100, 37.5% HCl by mass. All right. So, density can help us find a lot of stuff, but our two main definitions this time are concentration molality and concentration by percent. Okay. Hey, look, it's sulfuric acid. It has a density of 1.84 grams per milliliter and is 95% H2SO4 by weight. Calculate the molarity of the solution. Okay. Molarity is moles of solute per liter of solution. Molarity, moles over liters, right? Moles of what over liters of what? Okay, so what does 95% solution mean? That means that for every 95 grams of solution, there are 95 grams of sulfuric acid for every 100 grams of solution. So how can we use that information? Well, for A, we would say, well, that 95 grams of H2SO4 would be, because we want molarity, that would be 98.09 grams of H2SO4 for every 1 mole of H2SO4. We find out that we have 0.97 mole of sulfuric acid. All right, but we're not done because molarity is moles of solute per liter of solution. So we're going to have to use the density again here. So how can we use the density to find out what's going on? Well, this is our mass of solution. All right, the density of the solution is 1.84 grams. We can say, well, I have 100 grams of solution times the there's 1.84 grams of solution for every 1 liter of solution. And then, I'm sorry, for every 1 milliliter, because that's the density, grams per milliliter, but I just flipped it to cancel out. And then there's 1,000 milliliters for every liter. So this is going to be how many liters I have, and that's 0.054 liters. All right, so how do I get molarity? This 0.97 moles divided by 0.054 liters is 0.97 divided by 0.054 gives me 17.9. Oops, I got to round that up. 18.0 molar H2SO4. Okay, that's the concentration in molarity. The second question asks us to do the molality. So we already have our 0.97 moles. Woohoo, 0.97 moles. Right? It's moles of solute on top for molality every time. Okay. But now we have to find our kilograms of solvent. So how do we do that? I said solvent. This is kilograms of solution. I mean, that's grams of solution. So if this is solute, this is solution. 100 grams minus 95 grams means that there's 5 grams of solvent. All right. So if there's 5 grams of solvent, over on the side, 5 grams of solvent. I put kilograms because that's what I'm looking for. 5 grams of solvent times 1,000 grams for every 1 kilogram. Then I really have 0.005 kilograms. So 0.97 moles divided by 0.005 kilograms is, whoa, I think this is going to be a big number. 0.97 divided by 0.005, 194 mole solution. Okay, so here's our molality, here's our molarity, and it all came from percent and density. Okay, so, wow, that's a lot about concentration. Here's another thing that we can do with concentration. We can make solutions from other solutions. That's called dilution. So, in a solution, you know the number of moles, if you have molarity or molality. So, if you take some, we want to dilute something. So, we take our concentrated solution. Look at all those dissolved particles. We want to dilute it, then we take a little bit of this. So take a little bit of this, and we'll put it in this container. But then, to dilute it, we add more water. So the thing that happens is that however many moles we took from here, are still in there. The moles are equal. What's different is the amount of solvent. We want equal moles, so the formula we use for dilution is the molarity of our first solution times however much we took of it. The volume of it is still going to be equal to the molarity of our second solution times however much the volume of that is. Okay, so this might be small, and this might be small, and this might be big, and that might be small. This is smaller, but that's bigger. So as this goes up, that goes down. As this is the bigger one, but we're only using a little bit of it. Okay, so the moles on this side equal the moles on that side. So once we find out the amounts of concentrated acid we're using, we add water until we have the desired volume. That's important. Okay, so you take a little bit of this, put it in another container, and add water to the line. Add enough water to get to the line. Water to get blah 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 volume. Here's why. You can't add that much volume. You have to add water to get to that volume. Alright, so here, oh, someone's calling. So if we have a 4 molar solution of magnesium sulfate, okay, 4 moles for every liter of magnesium sulfate, how can we make 300 milliliters of 1.7 molar dilution, which is a diluted solution of magnesium sulfate? Okay, big molarity, so M1 is going to be our 4.0 molar. Okay, so the big one, we want to know, well, how much of that should we use to make our smaller one, right? And how much of the smaller one? We want 300 milliliters, but molarity is mole per liter. Even though we're going to cancel out units, let's change it to 300 to 0.3 liters. Okay. Oops, I would put a decimal point there on purpose. I always forget to do that. All right, so how do we solve this? Well, 4.0 molar. Here's the dilution equation. M1V1 equals M2V2, because moles have to be equal. So 4 molar times X is going to be equal to 1.7 molar times 0.300 liters. All right, so solve for this X. I can divide through by the 4.0 molar, 4.0 molar, and I find out that the X, if you look at molars cancel, we're left with liters, is 0.1275. X equals 127.5 milliliters. Okay, so just move a 3 to change it to milliliters. So what does this mean? All right, it means that I would take 127.5. Uh-oh, I better only take 100 and let's just make that. All right, I put a couple zeros in so we have sig figs. So let's just make this 128. Do sig figs. 128. Then we'll be right. Take 128 milliliters of 4 molar mag sulfate, magnesium sulfate. Put it in another container. Put it in another container. Then add water until you have 300 milliliters total. So the second solution will have the same number of moles that we took out of this solution, but we have more water because now we have 300 milliliters total. Okay, if you diluted 170 more 4 milliliters of 1.6 molar solution of lithium chloride to 1 liter, what's the new concentration? Okay, so we have an original molarity of 1.60 molar, and we only used 174 milliliters of it. We want to know what the new concentration is when we have 1.00 liters of it. Okay, so this time we're looking for the new concentration, and you should realize it should be smaller than the first one. All right, so 1.60 molar times 0.174 liters equals X molar for 1.00 liters. So what is X? Well, we divide through by the 1 liter. Yes, I know you guys will do that in your head, but I'm just showing you the work. Liters cancel. We're left with molarity. 1.6 times 0.174 is 0.278 molar. Okay, so the solution concentration of the second one is 0.278 molar, which is a lot less than the original concentration. Okay, last major topic is colligative properties. Colligative means collective. So these properties are determined by how much solute is in a solvent. It doesn't matter what the solute is, it just matters how much. So pure solvents like water and hexane and any other solvent has lots of properties. It has a boiling point, a melting point, a vapor pressure, etc. But when you add a solute to any pure solvent, it changes all of those properties. Why? Because the solute loves a solvent and wants to stay. More solute means more sting. I'll tell you what that means. There's three main places we see this in chemistry. Okay, one of them is called boiling point elevation, one of them is called freezing point depression, and the other one's vapor pressure depression. There's also one more I'll talk about quickly, but these are three that you should recognize. Okay, boiling point elevation. So you put ions into a solution and it makes the boiling point go up. Why? Because the solute loves solvent. So they stay together longer than they would if it was pure. The formula we're going to use to calculate the change in temperature is the change in temperature. The amount that the boiling point goes up is going to be equal to the Van 't Hoff constant. I'll explain in a second. The Kb for the solvent and the molality of the solvent. Delta T is change in boiling point. I is the Van 't Hoff constant, and Kb is the boiling point constant for water. Boiling point constant. It's for water. It is this. Okay. So let's do a problem. Well, let's find out what I is. I is the number of particles, but usually it's ions. So NaCl has an I of 2 because it has an Na plus and a Cl minus when it solves. CaCl2 has plus 2 and 2 chlorides. Okay, so that's going to matter. That's why the I is 3. Sugar only has an I of 1. Why? Because sugar only dissolves 1 for 1. Okay, when you put one sugar in, you get one sugar solute particle. Okay, so freezing point depression is the same kind of thing, except instead of the ions making the boiling point go up, now ions make the freezing point go down. Why? Solute loves solvent. Okay, so it wants to stay liquid longer and get in the way. The formula is almost exactly the same, except this time it's a Kf for a freezing point change. Okay, again, delta T is a change in the freezing point. I is a Van 't Hoff constant, and Kf is a freezing point constant. And this for water is 1.86 Celsius kilogram per mole. All right, so determine the change in boiling point for 300 grams of carbon disulfide, which has a Kb of that, if 35.5 grams of CH3Cl is dissolved in it. Okay, this is molecular, all covalent things, right? So we're talking about boiling point, so the change in temperature is going to be equal to the Van 't Hoff constant times the Kb times the molality of the solution. Well, molality is moles of solute per kilogram of solvent. So we need to change 35.5 grams of CH3Cl into moles. Where am I getting this? If you said periodic table, you are right. And I get 50.49 grams of CH3Cl for every 1 mole of CH3Cl. All right, so that's 0.703 moles of CH3Cl. Okay, now it's 300 grams of carbon disulfide, so that's the solvent. All right, but what do we have to do with that? We have to change it to kilograms. So 300 kilograms of CS2. Okay, why are these things dissolving? Because they're both covalent things. Okay, so then how do you figure out delta T? We have to plug in I. Oh, since this is molecular, I equals 1 because it doesn't break apart, so it's 1 for 1. The Kb is given to us, and it is 2.34 degrees Celsius kilogram per mole. All right, and the molality is, I never finished that one. The molality is 0.703 divided by 0.3 is also, interestingly enough, 0.703, 2.34, and that's moles per kilogram. This doesn't seem right. That cancels that. That cancels that. And we get to pause on that one. So I find out that my delta T, that times that, is going to be, let me just multiply this out, 1 times 2.34 times 2.34 is delta T equals 5.48 degrees Celsius. It was just interesting that that came out to be the same. So that means that if 46.2 degrees Celsius is the original temperature that it boils at, plus 5.48 degrees Celsius is the one it raises to, then we're going to get a new boiling point of 51.68 degrees Celsius. Okay, so the delta T is this. Okay, what's vapor pressure? Vapor pressure is the evaporated solvent, well, we'll say liquid particles that cause pressure on the surface. All right, so vapor pressure goes down. Vapor pressure goes down because solute loves solvent. All right, and they want to stay together. It's like, oh, look at this pink solute in the solvent. That wants to stay together, so there's less vapor pressure. Okay. Another one, osmotic pressure. Solvents are so attracted to the solutes, they will cross a semi-permeable membrane to get to them. So this is pure solvent. This has solute particles in it. So these solvent particles are like, we want to be with you, we want to be with you. So it'll cross a membrane to make that, to go with the solvent particles, solute particles. Okay, so to review, Boxing Hippo says know your formulas for molarity, molality, percent, concentration, and then delta T for boiling and freezing. Okay. When making solutions, don't add a specific volume of water. You always just fill until you get a volume of. Okay. Thanks, Boxing Hippo. Also to review, boiling point goes up, so don't, because the solute particles, solvent doesn't want to leave. Freezing point goes down because the solute gets in the way. We can find the delta T. And vapor pressure and osmotic pressure are colligative because the solvent is so attracted to solute, but there's no math. So make sure you can do all this stuff. We'll talk about this in class, okay? We can do that. We can do that. We can talk about colligative properties. We can calculate the boiling and freezing point. We're all set. I'll see you back in class. Don't forget to set your clocks forward. Peace out.